Okay, and we're back after being sick. I know everyone was really anticipating um, the return of this show. We're doing anatomy and physiology. The this is intro 1.5, homeostasis. By the end of this section, you will be able to discuss the role of homeostasis in healthy functioning, contrast negative and positive feedback, giving one physiologic example of each mechanism. Okay, maintaining homeostasis requires that the body continuously monitor its internal conditions. From body temperature to blood pressure to levels of certain nutrients, each physiological condition has a particular set point. First keyword. A set point is the physiological value around which the normal range fluctuates. A normal range, second keyword, is the restricted set of values that is optimally healthful and stable. For example, the set point for normal human body temperature is approximately 37 degrees Celsius, 98.6 degrees Fahrenheit. Physiological parameters, such as body temperature and blood pressure, tend to fluctuate within a normal range a few degrees above and below that point. Control centers in the brain and other parts of the body monitor and react to deviations from homeostasis using negative feedback. Negative feedback, that's our next key term here, is a mechanism that reverses a deviation from the set point. Therefore, negative feedback maintains body parameters within their normal range. The maintenance of homeostasis by negative feedback goes on throughout the body at all times with an understanding of negative feedback. And an understanding of negative feedback is thus fundamental to understanding of human physiology. This all makes sense to me so far. You've got the set point. It's like as I said, the physiological value around which the normal range fluctuates. So you have your set point, it's kind of like your midpoint. This is perfectly average. And then the range, and anything outside the normal range is when you start to get negative feedback. Yeah, cool. Negative feedback. Negative feedback system has three basic components. A sensor, that's a key term, also referred to as a receptor, okay, is a component of a feedback system that monitors a physiological value. This value is reported to the control center. Next key term. The control center is the component in a feedback system that compares the value to the normal range. If the value deviates too much from the set point, then the control center activates an effector. Okay. An effector is the component in a feedback system that causes a change to reverse the situation and return the value to the normal range. Okay, let's review that. You've got the sensor or receptor. You have the control center, and then you have the effector. So the sensor is actually picking up on what the current physiological value is. The control center compares it to the normal range. Sensor picking up what the data is, control center is processing it, comparing it to the normal range, and then the effector is a feedback system that starts to get homeostasis again if we are out of homeostasis. Okay, this makes sense. We have a little box here describing, I guess, an example. Stimulus, sensor, control, effector, response. And it's like a loop. Stimulus is the top of it, and then it causes the sensor, then the control, then the effector, then the response, and then that creates a stimulus again, I guess. Okay, here. Body temperature exceeds 37 degrees Celsius. Hey, welcome. We're talking about homeostasis. Body temperature exceeds 37 degrees Celsius. So the nerve cells in the skin and brain are the sensor for that. Then the control is the temperature regulatory center in the brain. Then they affect the sweat glands throughout the body. That's the effector. Sweating, oh my God, I was curious about this. That comes through the nerve cells in skin and brain. Good to know where that comes from. And then that increases heat loss. So it brings their temperature down. And we're back to homeostasis. Okay, cool. In order to set the system in motion, a stimulus must drive a physiological parameter beyond its normal range, that is, beyond homeostasis. The stimulus is heard by a specific sensor. For example, in the control of blood glucose, specific endocrine cells in the pancreas detect excess glucose, the stimulus, in the bloodstream. That's the stimulus, the excess glucose. Excuse me. These pancreatic beta cells respond to the increased level of blood glucose by releasing the hormone insulin into the bloodstream. The insulin signals skeletal muscle fibers, fat cells, adipocytes, and liver cells to take up the excess glucose, removing it from the bloodstream. Okay, let's review that. So, pancreas detects the stimulus, which is the excess glucose. Then the response is increased level of blood. Nope, sorry. The response is to release insulin into the bloodstream. The insulin tells the skeletal muscle fibers, fat cells, and liver cells to take excess glucose and remove it from the bloodstream. Cool. As glucose concentration in the bloodstream drops, the decrease in concentration, the actual negative feedback, is detected by pancreatic alpha cells, and the insulin release stops. This prevents blood sugar levels from continuing to drop below the normal range. Okay. Humans have a similar temperature regulation feedback system that works by promoting either heat loss or heat gain. When the brain's temperature regulation center receives data from sensors indicating that the body's temperature exceeds its normal range, it stimulates a cluster of brain cells referred to as the heat loss center. This stimulation has three major effects. Blood vessels in the skin begin to dilate, allowing more blood from the body core to flow to the surface of the skin, allowing the heat to radiate into the environment. So I guess we release more heat and stop preserving it, I guess would be the translation for me. As blood flow to skin increases, sweat glands are activated to increase their output. As the sweat evaporates from the skin surface into the surrounding air, it takes heat with it. The depth of respiration increases, and a person may breathe through an open mouth instead of through the nasal passageways. This further increases heat loss from the lungs. Okay. In contrast, activation of the brain's heat gain center by exposure to cold reduces blood flow to the skin, keeps it in the core, and blood returning from the limbs is diverted into a network of deep veins. This arrangement traps heat closer to the body core and restricts heat loss. If heat loss is severe, the brain triggers an increase in random signals to skeletal muscles, causing them to contract and produce shivering. The muscle contractions of shivering release heat while using ATP, so it uses a lot of energy. The brain triggers the thyroid gland in the endocrine system to release thyroid hormone, which increases metabolic activity and heat production in cells throughout the body. The brain also signals the adrenal glands to release adrenaline, but they call it epinephrine. I'm taking a guess. A hormone that causes the breakdown of glycogen into glucose, which can be used as an energy source. The breakdown of glycogen into glucose also results in increased metabolism and heat production. Okay. Positive feedback, next section. So we have negative feedback, now positive. intensifies a change in the body's physiological condition rather than reversing it. A deviation from the normal range results in more change. Yes, and the system moves farther away from the normal range. Positive feedback in the body is normal only when there is a definite endpoint. Okay. Childbirth and the body's response to blood loss are two examples of positive feedback loops that are normal but are activated only when needed. I'm very curious how this works. Childbirth at full term is an example of a situation in which the maintenance of the existing body state is not desired. Okay, right. This is not homeostasis. We want the baby out. Okay. Enormous changes in a person's body are required to expel the baby at the end of pregnancy. And the events of childbirth, once begun, must progress rapidly to a conclusion, or the life of a person giving birth and the baby are at risk. The extreme muscular work of labor and delivery are the result of a positive feedback system. Okay, interesting. The first contractions of labor, the stimulus, push the baby towards the cervix, the lowest part of the uterus. The cervix contains stretch-sensitive nerve cells that monitor the degree of stretching, the sensors. These nerve cells send messages to the brain, which in turn cause the pituitary gland at the base of the brain to release the hormone oxytocin into the bloodstream. Oxytocin causes stronger contractions of the smooth muscles in the uterus, the effectors, pushing the baby further down the birth canal. This causes even greater stretching of the cervix. The cycle of stretching, oxytocin release, and increasingly more forceful contractions stops only when the baby is born. At this point, the stretching of the cervix halts, stopping the release of oxytocin. A second example of positive feedback centers on reversing extreme damage to the body. Following a penetrating wound, the most immediate threat is excessive blood loss. Less blood circulating means reduced blood pressure and reduced perfusion penetration of blood to the brain and other vital organs. If perfusion is severely reduced, vital organs will shut down and the person will die. The body responds to this potential catastrophe by releasing substances in the injured blood vessel, that wall, that begin the process of blood clotting. As each step of clotting occurs, it stimulates the release of more clotting substances. This accelerates the processes of clotting and sealing off the damaged area. Clotting is contained in a local area based on the tightly controlled availability of clotting proteins. This is an adaptive, life-saving cascade of events. And that is 1.5. So just to review, homeostasis works with negative feedback or positive feedback. Negative feedback is a reaction that tries to return to homeostasis. Positive feedback accelerates away from homeostasis for the end goal of maybe having a baby, maybe stopping a wound from bleeding. Okay, cool. Good information, guys. Thanks, everybody.